This is the Chapter 9b PowerPoint. In Chapter 9a, we spoke of air masses and their characteristics and their source regions and how they invade North America, either from Canada or the North Pole or the Gulf of Mexico, the oceans adjacent, and so on. Now we're going to talk about weather fronts. A weather front or a front is a transition zone between two air masses of differing characteristics, differing densities. Now, since density differences in air masses are most often caused by temperature differences, fronts usually separate air masses with contrasting temperature and humidity. Fronts in the atmosphere have both horizontal and vertical extent, but we often show weather fronts on surface weather maps in two dimensions like this. So be aware that it's not just a two-dimensional thing, they have vertical as well as horizontal extent. This is figure 9.16 from your textbook, which shows a typical weather front system that might be moving through North America. And you can see on the right there is a simplified key for identifying things like cold fronts, stationary fronts, warm fronts, occluded fronts, and symbols for weather depiction like light snow, the little asterisk there, light rain, the two dots. And then each place where weather data is observed at an airport is called a station model. And there is an international code that's established so that anybody who looks at that station model can tell what the weather is like. For instance, that place over in eastern Colorado that has a -8 and a -12, that's the temperature and dew point respectively, and since the circle isn't filled in, they have clear skies, and the winds are coming from the southeast at 10 miles an hour. That's that little stick with a flag on it. Over time, you'll learn more about those weather symbols. Refer to Appendix C in the back of the book, which will decipher a lot of these for you. How do meteorologists identify weather fronts on a surface weather map? Well, they look for sharp changes in temperature, sharp changes in dew points, that's the moisture content of the air, a shift in the wind direction, sharp changes in atmospheric pressure, rising or falling, the kinds of clouds present and precipitation that may or may not be going on, and whether a front is weakening, which is frontalysis, or strengthening, or actually forming, which is called frontogenesis or frontogenesis. Now we'll talk first of all about the kind of front known as a stationary front. A stationary front essentially has no movement. There's a stalemate between the opposing air masses. The cold air is not advancing, taking over the warm air mass. The warm air mass is not advancing and overtaking the cold air mass. Stationary fronts in North America often separate continental polar air and maritime tropical air, or continental polar air and maritime polar air. They are shown in the weather map with the alternating red and blue lines, as you saw in the previous couple of slides. Now, in the case of the slide with that big weather map of the U.S. that I showed you, line AB is the stationary front. And in this case, you don't see any active weather. You don't see rain or snow shown there. Sometimes there may not be any clouds or active weather with a stationary front. It just might be a difference in temperature. For instance, east of the Rockies, there is continental polar air, and west of the Rockies, in this case, there's maritime polar air. And the Rocky Mountains often, in winter and early spring, act as a geographical barrier between these air masses. And so it's typical, based on the observations at the airports, to draw a stationary front, which basically straddles the crest of the Rocky Mountains. Now, sometimes you can have very, very active weather with stationary fronts. Now, let's go to cold fronts. This is figure 9.18, which is a close-up of the cold front in figure 9.16, and it appears that this cold front is straddling the state of Tennessee. So you can see to the south there, you can see basically Arkansas. You can, off on the left-hand side of the map, you see Arkansas, a little corner of extreme northeast Louisiana. You see northern Mississippi, northern Alabama, Tennessee, Kentucky, and then a little piece of what appears to be Illinois, and then southeast Missouri. So this close-up of this cold front, if you really look at that, you can see tremendous contrasts in conditions. You got temperatures in the mid to upper 50s Fahrenheit in the advance of the cold front. There's that place in northern Mississippi which has 50 degrees, a southwest wind at 15 miles an hour with the little red arrow symbol. That's a thunderstorm. And then you look on the other side of that cold front. Check out northern Kentucky, that place that has 32 degrees and has white shading over it. It's snowing there. So obviously the cold air mass is overtaking and replacing the warm air mass. And note the line XX prime, because the next graphic is actually a cross-section of that a vertical view of the weather that you would expect if you were along that line and the cold front were advancing on your location. A dramatic change as a cold, heavy, blustery air mass overtakes and pushes out of the way a warmer, moist air mass and lifts it along the front, causing those towering clouds and thunderstorms depicted in this graphic. Again, I point out to you the big contrast in temperatures, with 50s Fahrenheit ahead of the front and 20s, 30s, and lower 40s behind the cold front after it goes through. Figure 9.17 shows clouds which are approaching in the advance of a cold front, towering clouds as the warm, moist air is rapidly lifted upward by the cold air, which is heavier on the surface, lifting that warm, moist air upward, causing those towering clouds. Figure 9.19 shows a typical radar composite graphic from one of these kinds of cold fronts that might be going through this part of the country. It's not exactly the same cold front, but notice the yellows and reds on that map, which indicate moderate to heavy precipitation and probably some thunderstorms right in the advance of that cold front. With cold fronts, the cold, dense air wedges up under the warm, moist, less dense air and actually forces it upward like a wedge. Now, a fast-moving cold front might have a slope of 1 to 50, meaning that for every 1 kilometer you go up, you're going 50 kilometers on the surface in the horizontal. That's a steep, powerful cold front. A slower-moving cold front may have a gentler slope, not a steep slope like 1 to 50. It might be 1 to 100. In the advance of cold fronts, especially east of the Rockies, it is not uncommon to have a line of very strong thunderstorms preceding it, and that is called a squall line. If the temperature contrast between one side of the weather front and the other starts to lessen, then the front might be weakening, and the meteorological term for that, the weather speak term for that, is frontolysis. If the temperature contrast on either side of the cold front increases, the front may be strengthening. We call that frontogenesis or frontogenesis. Now, in the previous panels about cold fronts, we've described typical cold fronts as they cross mostly the central and eastern United States. Sometimes, though, cold fronts east of the Rockies move so fast that warm air coming from the Gulf of Mexico, maritime tropical air, doesn't even have a chance to develop ahead of it. Here on the West Coast, we have some special cases because the Pacific Ocean modifies our temperatures so much that it's really hard to find the position of the cold front in some cases. Table 9.2 on page 256 describes typical weather conditions associated with a cold front passing through parts of the northern hemisphere, specifically North America, because that's what we're focusing on here. Here is a case study of a cold front that was weakening over land because of lowering temperature contrast between one side of the front and the other. Then the next day, that front goes over the Atlantic Ocean, picks up warmth and moisture from maritime tropical air ahead of it, and then actually starts to strengthen. You notice that there are more clouds associated with the system in the panel on the right, and they've got the little thunderstorm symbol along the cold front, which means that certainly this front is beginning to experience frontogenesis. In New England, sometimes they can get what's called a backdoor cold front, as maritime polar air can plunge southwestward from the maritime provinces of Canada along the east coast to southeast coast of Canada, and can make for big contrasts in temperature, especially in the spring. You notice the 75-degree temperature ahead of the cold front in Philadelphia. I think that's where that is. And then the place in Connecticut has a 45-degree temperature. So that must have been a very abrupt change for people in New England on that particular spring day. This is a depiction of a particularly strong cold front, which is going through extreme western Illinois, extreme eastern Iowa, slicing Missouri diagonally, and then going through western Arkansas. The green means rain, the pink means mixed precipitation or freezing rain, and then the white means snow. Notice the 63-degree temperature Fahrenheit in St. Louis compared to the 1-degree Fahrenheit temperature over on the left-hand side in Concordia, Kansas. So within just a 500-mile swath, you can see a tremendous contrast in temperature between one side of that front and the other. Must have been a real shock for those people in Missouri to wake up to warm rains in the morning and have snow by dinner time. Must have been a real shock to them on January 18, 1996. Here is a recent example that I actually saw on a map and captured it for this purpose. These are weather observations at airports over Texas, Louisiana, Arkansas, Oklahoma, and extreme eastern New Mexico. on Wednesday, December 19th, 2012 at 4 o'clock p.m. Central Standard Time. That's 2 o'clock in the afternoon our time. But I want you to go down the border of Texas and Mexico and find that place called FTN that has a temperature of 90. Okay, that's kind of warm for December, I think, for anywhere in the U.S., you would agree. And then you go to the northern part of the Texas Panhandle, way up there, and you see that 32? So the 90-degree temperature is in a town called Dimmitt, Texas. The 32-degree temperature is in a town called Dalhart, Texas. So somewhere in there is a cold front. Can you draw it? Can you draw where the cold front is? I'll bet you can. I think it's kind of a no-duh. By the way, there are some places in Texas that have blowing dust in the advance of that cold front. So it was a very interesting day, Wednesday, December 19th, 2012. Now let's talk about warm fronts. Warm front is where warmer air is advancing and is replacing colder air. You can notice a close-up of this warm front. In its advance, you see snow and then mixed precipitation or sleet or freezing rain or rain and snow mixed. That's the pink. And then the green depicts rain, and then the warm front moves through and it clears up and warms up. Notice the 20s and 30s in the advance of the warm front and the temperatures in the upper 40s and 50s Fahrenheit behind the warm front. So here, warm air is pushing cold air out of the way. Now, sometimes at night, radiational cooling can slow a warm front's forward movement. This figure, 9.24 on the right, has a line on it. Can you see it? It goes P prime, all right? And so what I'm going to do now is switch to the next slide, which is essentially a vertical view or cross-section of that line and the kind of weather that would be experienced perhaps by an observer if you were in an aircraft and you flew along that line. Obviously, in the advance of the warm front, it would be colder with frozen precipitation, which would then change to rain. There might be fog right associated with the warm front, and then the warm front goes through and it clears up and it warms up and the wind shifts. So that's a little bit about warm fronts. Now, what's happening here, of course, is that the warm front acts as a wedge to lift skyward the colder air. This is cloud cover and precipitation that increases, which is often referred to as overrunning. This can cause clouds and precipitation to actually be observed well in advance of the surface passage of the warm front. Warm fronts have much gentler slopes compared to cold fronts, like about 1 kilometer in the vertical to 300 in the horizontal. Now, it's a lot harder to find warm fronts on the West Coast because the Pacific Ocean tends to modify the air. Table 9.3 on page 259 outlines typical conditions as warm fronts pass through the Northern Hemisphere. Next kind of a front is a dry line. A dry line separates air masses of differing dew points mostly. Notice the temperatures and dew points east of the dry line. You've got 80s for temperatures, upper 80s, and dew points near 70. Behind the dry line, you've got temperatures 90s to low 100s and dew points in the 20s and 30s. So a dry line separates warm, moist air from warm, dry air. This is true in the spring and early summer when continental tropical air masses form over northern Mexico as it starts to get hot as the seasons change. And along dry lines, you can get quite a bit of lifting, which can often produce severe thunderstorms. We'll talk more about that in a future chapter. Then there are occluded fronts, which are very complicated because cold air moves faster than warm air. Part of the cold front catches up with part of the warm front and forms an occlusion. If you look at this graphic from bottom to top, stage A, stage B, stage C, you can see how an occlusion forms. This is a cold occlusion because the air behind the occlusion is colder than the air in advance of it. This is a warm occlusion, which we often get on the West Coast. And again, look at the graphic from bottom to top, A, B, and C, where actually air that's not quite as cold as the air over the land moves in from the Pacific Ocean. And then that part of the cold front again collides with part of the warm front, forms an occlusion. But this is a warm occlusion because it's maritime polar air taking over continental polar air. So it's kind of the reverse of the previous situation. This table shows typical conditions associated with occluded fronts as they pass through North America. There's a front that is not drawn on surface weather maps because it's called an upper level front. Basically, colder, drier air as it's sinking can lift warm, moist air in its advance, even before that upper level front even reaches the surface, but can act like a wedge to actually lift that air mass up and produce showers and thunderstorms. This is a full-on mid-latitude cyclone with a warm, cold, and occluded front, which we'll study in much more detail as we start Chapter 10.